Assalamu alaikum, hello everyone, and welcome back to the good stuff. We are continuing and we have reached the last part of our second topic, chemical families. In this topic, we will cover noble gases, group 8 and group 7 halogens. So, without further ado, let's dive straight into it. We will start with noble gases because it is a relatively short area, after which we can cover halogens, which is kind of long. So, noble gases. Noble gases are group 8 elements. They are stable. As we learned in primary, also in science, noble gases, the main noble gas is argon. However, we have helium, so argon comes after helium. Helium is first. Then we have neon and argon. However, below in the periodic table, these are elements which are not discussed. We have krypton and xenon. However, these two are not discussed in our syllabus for now, but helium, neon, and argon are the ones we should be looked at. Now, these three noble gases, helium has valencio, it has is helium is number 2 in the first 20 elements, so it has a duplet state, a stable duplet state. Neon has 2 8, it is number 10, and argon being number 18 has 2 8 8. So what do we know from this? We know that these gases are chemically stable. They are stable, hence they do not easily react. So except helium, they have 8 electrons in the outermost energy level, as I just showed you. Out of all the noble gases, which one is the most abundant? Argon is the most abundant. Out of noble gases form 0.97% of the atmosphere of the air. However, of this 0.97%, 0.9% is argon, which makes argon the most abundant noble gas. Noble gases show an increase in atomic radius, as I told you in the previous lesson, in all the groups in the periodic table. Every group, the trend shows an increase in atomic radius due to increase in number of energy levels. Atomic radius increases due to an increase in number of occupied energy levels. They have very high ionization energies. The noble gases require a lot of energy to lose electrons because they are already stable. They already have octet stability. So for a noble gas to lose an electron, it requires a lot of high ionization energy. So they have very high ionization energies because they are stable. And that is with noble gases. We go to physical properties. Physical properties and the uses. So physical properties. They are colorless, odorless gases. They are colorless and odorless gases. What is colorless? Colorless lacks color and odorless lacks smell. So noble gases, e.g. argon, helium, they don't have smell and they don't have color. They have low melting and boiling points. Low melting and boiling points, MP and BP, since they have weak van der Waals forces of attraction. Weak van der Waals forces of attraction. Van der Waals forces of attraction are taught in structure and bonding. Melting and boiling point increase down the group due to an increase in atomic radius, hence decrease in van der Waals forces. They are monoatomic gases. So number 3 we have monoatomic. As we saw, the other gases such as chlorine, oxygen, hydrogen are diatomic, hence written as H2, O2, Cl2. But noble gases are monoatomic, they only exist as one molecule. So they are monoatomic. So argon is not written as Ar2. No. Argon is, this is wrong. Argon is just written as Ar. And so is helium, He. Xenon, Xe. Neon, Ne. They are monoatomic, hence written as a single unit. Number 4, which is leading us to the melting and boiling point increase down the group. Melting and boiling point increase down the group. Why? Due to an increase in atomic radius, hence increase in molecular mass. The melting and boiling points increase down the group due to an increase in atomic radius, hence increase in molecular mass. We go to uses of noble gases. Helium is used in hot air balloons because it is light and non-flammable. Is used in hot air balloons because it is light and non-flammable. Also, argon is fitted in electric bulbs to prevent oxidation of filament. You only have to know a maximum of 2 or 3 uses. So argon is fitted in light bulbs to prevent oxidation of filament. Because it is inert. What do I mean by inert? Inert means it is non-reactive. Argon being stable, having an electron configuration of 2,8, having octet stability, it is very difficult for argon to react because it does not lose or gain any electrons. Since it is inert, it prevents the oxidation of filament. The filament does not react with oxygen, hence it secures the filament and prevents its oxidation. Neon is used in decorative or disco lights. Neon is used in decorative stroke disco lights. Another use of helium is it is mixed with oxygen gas and used in deep sea diving. Helium He is mixed with oxygen and used in deep sea diving. Deep sea diving. So these are the uses of noble gases. Helium is used in hot air balloons because it is light and unflammable. Argon is fitted in light bulbs to prevent oxidation of filament because it is inert. Neon is used in decorative lights. Helium is mixed with oxygen and used in deep sea diving. And that marks the end of noble gases. Now we go to a rather long area, halogens. Our chemical family, halogens. Halogens is group 7. The group is group 7, but the name of the chemical family is halogens. Have halogens. These are group 7 elements. We have chlorine, bromine, iodine, and astatine. However, in the periodic table, we have only 2 halogens. We have chlorine and bromine. These two are outside the first 20 elements, but iodine may be, sometimes it will be questioned and discussed. So the electron configuration, there is fluorine also. We have fluorine, chlorine, bromine, iodine, and astatine. So fluorine written as F has an electron configuration of 2, 7. Chlorine is 2, 8, 7. Bromine is 2, 8, 18, 7. And as you saw the formula for energy levels 2n squared, you can calculate the third energy level can occupy how many electrons in iodine and astatine, but that is not necessary. So fluorine, chlorine, and bromine, we know the electron arrangements Cl and Br. These two are gases at room temperature. Bromine is a liquid and iodine is a solid. So at room temperature RT, fluorine and chlorine are gases. Bromine is a liquid and iodine is a solid. Atomic properties of halogens. Atomic properties of halogens. Atomic properties. Atomic and ionic radii. Atomic radius, number 1, atomic radius increases down the group due to an increase in number of occupied energy levels. Same for ionic radius. Ionic radius also increases down the group due to an increase in number of occupied energy levels. However, if you compare ionic radius and atomic radius of halogens, the ionic radius of halogen is greater than the atomic radius of the same halogen. Why? This is because how do halogens become chemically stable? Having an electron arrangement of 287 for chlorine, how does it become chemically stable? The third energy level, the last energy level, gains an electron to form 288. However, what's the number of protons in this element? We have 17 protons, but now how many electrons do you have? 18 electrons. So as we said, protons are the one that cause the nuclear force of attraction. In this case, the electrons are more than the protons, hence there is a weaker nuclear force of attraction. So I won't write this, but mind my explanation. The ionic radius of a halogen of chlorine is greater than the atomic radius of chlorine. Why? This is because on gaining an electron, a chlorine ion has more electrons than protons, hence a weaker nuclear force of attraction. The chlorine ion, this is the chlorine atom and this is the chlorine ion. On gaining an electron, the electrons become more than the protons. The protons remain 17, but the electrons become 18. So the electrons become more than the protons, hence a weaker nuclear force of attraction. Or another explanation is the ionic radius is larger than the atomic radius since they react by gaining one electron. Hence the gained electron is repelled by the existing electrons, the ion bulges out. What do I mean by this? We have a chlorine atom here. Let me just draw the outermost electrons. We have 7 outermost electrons which are negatively charged. Now if this atom gains one electron, a dot here, this electron will be repelled. It is negatively charged. It will be repelled by the existing electrons which are negatively charged. Hence, the ion will bulge out to accommodate the gain electron. I explain again. The ionic radius is larger than the atomic radius. This is because chlorine reacts by gaining one electron. Hence, the gained electron is repelled by the existing electrons. The ion bulges out. Or chlorine reacts by gaining one electron. Hence, the electrons become more than the number of protons, which leads to a weaker nuclear force of attraction. You can use any of the two explanations. Reactivity. Now I need you to focus on this area very carefully. Reactivity. This is not the same as alkali metals and alkaline earth metals. It is the complete opposite. Why? As we saw, alkali metals and alkaline earth metals react by losing electrons. The same way, chlorine and halogens react by gaining electrons. So the reactivity of halogens is different, the trend is different. In alkali metals, reactivity increases down the group due to an increase in atomic radius, weaker nuclear force of attraction. The valence electron can be easily lost. However, in halogens, the reactivity decreases down the group. Why? Understand this now. We have a fluorine atom here. This is a fluorine atom, and we have a chlorine atom here. This is 2,7. And 2,8,7. This is a fluorine atom, this is a chlorine atom. Which atom has a large atomic radius? Of course, the chlorine atom with 3 energy levels, then the fluorine atom has only 2 energy levels. Now, as we said, halogens react by gaining electrons. For which atom here is it easier to gain an electron? For the fluorine atom. If this was the same with alkali metals, we would have said the chlorine it is easier for it to lose an electron. But in halogens, they react by gaining electrons. Fluorine gains an electron more easily than chlorine. Why? This is because fluorine has a smaller atomic radius, hence a stronger nuclear force of attraction. The valence electron can be easily gained. Now mind the contrast in halogens and alkali metals. In alkali metals, we said larger atomic radius, weaker nuclear force of attraction, the valence electron can be easily lost. In halogens, smaller atomic radius, stronger nuclear force of attraction, the valence electron can be easily gained. So reactivity decreases down the group. Why? Reactivity decreases down the group. Due to an increase in atomic radius, hence weaker nuclear force of attraction. Nuclear force of attraction. The valence electron cannot be easily gained. Let's come together on this. Reactivity decreases down the group. Why? Due to an increase in atomic radius. The atomic radius increases, the nuclear force weakens, hence the valence electron cannot be easily gained. Oxidizing property. As we said, alkali metals and alkaline earth metals are reducing agents. The same contrast in halogen is that they are oxidizing agents. So the oxidizing property also compares with the reactivity and it decreases down the group. Why? Due to an increase in atomic radius, hence the valence electron cannot be easily gained. Electronegativity. In alkali metals, we learned something called electropositivity, the ability of an atom to lose an electron and become positively charged. However, here we will learn electronegativity. Electronegativity is the ability of an atom to gain an electron and become negatively charged. Negativity means it gains an electron and become negatively charged. Ability of an atom to gain an electron and become negatively charged. Electronegativity, does it increase down the group or decrease down the group? Electronegativity also decreases down the group. Why? Due to an increase in atomic radius, hence weaker nuclear force of attraction, the valence electron cannot be easily gained. So it is difficult to gain an electron and become negatively charged. So the electronegativity of an atom in halogen decreases down the group. Then we go to electron affinity. Electron affinity is the opposite of ionization energy. I repeat, electron affinity is the opposite of ionization energy. Why? Ionization energy is the minimum amount of energy required by an atom in gaseous state to lose an electron. But electron affinity is the minimum amount of energy required by an atom in gaseous state to gain an electron. Minimum energy required by an atom in gaseous state to gain an electron and become stable. You can include that or you cannot include that. So electron affinity also increases down the group. Electron affinity is ionization energy. Now as you can see, if you compare every aspect with each other in alkali metals and halogens, in alkali metals, ionization energy decreases down the group. Due to an increase in atomic radius, weaker nuclear force of attraction, the valence electron can be easily lost. However, electron affinity, it increases down the group. Why? Due to an increase in atomic radius, weaker nuclear force of attraction, the valence electron cannot be easily gained. In alkali metals, you are losing an electron, but in halogens, you are gaining an electron. So electron affinity also increases down the group. Melting and boiling points. So the electron affinity of chlorine is more than the electron affinity of fluorine. Why? Because chlorine having a large atomic radius than fluorine, weaker nuclear force of attraction, the valence electron is not easily gained. It requires more energy. So the last atomic characteristic is melting and boiling point, MP and BP. This increases down the group due to an increase in atomic radius, hence increase in molecular mass. Increases down the group due to an increase in atomic radius, hence increase in molecular mass. An increase in molecular mass leads to an increase in van der Waals forces of attraction. Hence, it requires more energy or more heat to break the van der Waals forces. Hence, an increase in melting and boiling points. Note by halogen exist as the atomic molecules, e.g. F2, fluorine F2, chlorine Cl2, bromine Br2. The molecules are held by weak van der Waals forces of attraction. Now, van der Waals forces of attraction are covered in structure and bonding, but in this topic, you will just know the melting and boiling points increase down the group due to an increase in atomic radius, hence an increase in molecular mass. Physical properties of halogens. Physical properties of halogens. Halogens are non-conductors of electricity. Non-conductors of electricity since they lack delocalized electrons. And secondly, halogen vapors are poisonous. Chlorine gas, when inhaled in a high amount, can be poisonous to the human body, and so is fluorine. So halogen vapors are poisonous. And as I already told you, fluorine and chlorine are gases at room temperature. Bromine is a brown liquid at room temperature, and iodine is a black solid at room temperature. Fluorine is yellow in color, chlorine is green, bromine brown, and iodine is black. Preparation of chlorine gas. Now, chlorine is the main halogen that is discussed in halogens. It is the main. So, preparation of chlorine gas. We must know how to prepare chlorine gas. Preparation of chlorine gas. Preparation of Cl2 chlorine gas. So, this is the preparation of chlorine gas. The reactants for preparation are concentrated hydrochloric acid and oxidizing agent such as manganese 4 oxide or potassium manganate 7. All this will be taught in the topic chlorine and its compounds, and it will be taught by me again. But I am just touching on this area so you know the preparation of chlorine gas. In this funnel there is hydrochloric acid placed, concentrated hydrochloric acid, and here down there is manganese 4 oxide. Manganese 4 oxide written as MnO2. MnO2 is manganese 4 oxide. There is water here which absorbs traces of hydrogen chloride gas. Water absorbs traces of hydrogen chloride gas. Now this all will be stressed in chlorine and its compounds. Concentrated sulfuric 6 acid dries the chlorine gas. When manganese 4 oxide react with hydrochloric acid, it gives traces of hydrogen chloride gas from the HCl acid, and the chlorine gas, when it passes in H2SO4, concentrated sulfuric 6 acid, the gas is dried and it is collected by downward delivery. It is collected by downward delivery since it is denser than air. So this is the setup for collection of chlorine gas. Now you have to know the chemical equation for preparation of chlorine gas. This took me long to draw, but it's okay as long as you understand. So the equation for the reaction is manganese 4 oxide MnO2 solid plus hydrochloric acid concentrated, which is AQ, to form manganese chloride, AQ plus water plus chlorine. Manganese oxide reacts with HCl to form manganese chloride plus water plus chlorine. Is this equation balanced? It isn't. So we will have to balance this equation. 3. No, I will balance this later. There's no need to do it right now. Chemical properties. So this is the equation. We will balance the equation later on in the topic chlorine and its compounds, but you can balance it for yourself. I want to move on to chemical properties. And note, instead of manganese oxide in the setup for preparation of chlorine gas, if potassium manganate 7, which is a stronger oxidizing agent, is used, hence no heating is required. But in the other setup, you have to draw 2 arrows to heat the mixture for the reaction to occur faster. Chemical properties. Chlorine reacts with water to form chlorine water, while bromine forms bromine water. Now note this, chlorine reacts with water to form chlorine water. What is chlorine water? Chlorine water is HCl plus HOCl. Now this is hydrochloric acid and this is hypochlorous acid. HOCl is hypochlorous acid or chloric-1 acid. Hypochlorous or chloric-1 acid. What is the color of this mixture? It is pale yellow. Chlorine water is pale yellow and bromine water is pale yellow too. So instead of chlorine water, you can have bromine water. So instead of Cl2, you put Br2 plus water to form HBr plus HOBr. This equation is balanced. This is pale yellow. Chlorine water is pale yellow in color due to presence of HOCl. Chlorine water is pale yellow due to presence of HOCl, chloric-1 acid. When a blue litmus paper is dipped in chlorine water, it changes to red due to HCl, which is acidic, and then it is bleached due to HOCl. So this HOCl we saw, HOCl, hypochlorous acid or chloric-1 acid, is a bleaching agent. It bleaches moist red litmus paper too. It bleaches moist red litmus paper. It bleaches moist blue litmus paper. The moist blue litmus paper changes to red and then it is bleached. Why? Due to the presence of HCl, which is acidic, and HOCl, which is a bleaching agent. I repeat, when a blue litmus paper is dropped in chlorine water, it changes to red due to HCl, which is acidic, then it is bleached by HOCl. And what is bleaching? It is the whitening of a substance by oxidation or reduction. So the moist blue litmus paper changes to red due to HCl and it is bleached due to HOCl. Bleach action of chlorine water. Chlorine gas bleaches when there is moisture. This is due to the presence of HOCl, which oxidizes the dye in litmus paper, hence bleached. Now what is the equation for bleaching? HOCl is the one that bleaches, isn't it? Plus dye. Dye is the one that is bleached in the litmus paper. Form dye plus O plus HCl. What am I representing by this? HOCl is the bleaching agent. Dye is the one which is being bleached. Now HOCl bleaches dye by oxidation. Chlorine, the bleaching action of chlorine is by oxidation. So dye gains oxygen, it is oxidized by HOCl, which loses this oxygen, it gives it to dye and HCl. Now if this color was pink, this is white, this dye, let's say this color is pink or red or any other color, dye plus O is white. Why? Because this substance has been bleached by HOCl, and the resultant, when HOCl loses this oxygen to die, the resultant is HCl. The test for chlorine gas, I won't be writing everything, so you can write it for yourself. The test for chlorine gas is that it bleaches moist blue litmus paper. It changes moist blue litmus paper to red and then bleached. It changes to red due to presence of HCl and then bleached due to presence of HOCl. Effect of sunlight on chlorine water. This is a very much tested area. Effect of sunlight on chlorine water. You can have a jar over here, and effect of sunlight on chlorine water. Now let's say this is chlorine water. What is the observation of sunlight? There is sunlight decomposing this chlorine water. What is the observation? The observation, there is effervescence of a colorless gas that relights a glowing splint, which is oxygen, and secondly, it changes the color of chlorine water from pale yellow to colorless. Why? Pale yellow is HOCl. However, HOCl is decomposed to form HCl and oxygen. This is the equation. HOCl decomposes to form HCl and oxygen. So, the first observation, write this down. The first observation is the pale yellow color of chlorine water decolorizes or changes to colorless, and the second is a colorless gas is collected which relights a glowing splint. This gas is oxygen. We have oxygen collected over here. Reaction with metals. A halogen reacts with a metal to form a metal chloride or a metal bromide. So zinc reacts with chlorine to form zinc chloride. Magnesium reacts with chlorine to form magnesium chloride. Now we mark the end of our lesson with the effect of sunlight on chlorine water. We will continue from there. We are left with a few notes and uses of halogens, which we will cover at the start of next lesson. And the next lesson we will cover the topic salts. So until then, goodbye, take care, thank you for watching, have a good day.